That's fine.
Thank you, Eliezer. Well, we've got one more speaker for today, and that is none other than Max Tegmark, professor at MIT. Before becoming a professor at MIT, he was a research associate at the Max Planck Institute for Physics in Munich, Germany, a Hubble Fellow at Princeton's Institute for Advanced Study, and a faculty member at the University of Pennsylvania. Professor Tegmark's research has focused on cosmology theory and phenomenology, but has also included diverse topics, including interpretations of quantum mechanics, predictions of inflation, and parallel universes. He advocates the mathematical universe hypothesis, where our external physical reality is assumed to be purely mathematical. He has over 200 publications, of which 9 have been cited over 500 times. Today, he will present a cosmological perspective on the future of intelligence, assess the likelihood that Earth-based life will one day spread across space, and explore what can be done to give our species' long-term prospects greater weight in contemporary decision-making. Please welcome, to close day 1 of the Singularity Summit, Professor Max Tegmark.
Thank you so much. Thank you so much. It's a great pleasure to be here. Do you want to press the magic button there to get my display up on the screen? There we go. Yeah, so I've been called upon to talk about a cosmic perspective on the future of life. We've heard a lot of exciting discussion here about the next century and even shorter times. I want to talk more about the next giga-year, or the many billions of years that lie ahead. So we have all together, as humans, been walking down this path of life here, and it's very natural for us to wonder what lies around the corner. We've heard a lot of different discussions about different possibilities, some very encouraging, some saying more or less we're going to keep going in the same style as we're doing now. Others say maybe we can eventually have life evolve, improve, engulf maybe our entire universe. Others say maybe life will also change its very nature to some other form, and some are more optimistic about this. Others envision more dystopian scenarios. So what's it going to be? Or maybe we'll just wipe ourselves out. There's no shortage of ideas for that. For the cosmological perspective, let's begin by just reminding ourselves very briefly about what we've learned so far about our place in space. And if we could for a moment just get things really nice and dark in here, I want to take you for a little ride. So as we zoom closer to home here, let's just remind ourselves of the basic scales of things. It takes about 8 minutes for light to go from the sun out to the radius of Earth's orbit. We know that it takes several hours for light to get to the outer solar system. So if you're having a cell phone conversation with your friend on Pluto, it's kind of boring. You're like, hey, how's it going? And 3 hours later, they hear you. 6 hours later, you hear back. And yet, of course, this is tiny compared to the distances to the nearby stars. This is not a computer simulation, but a real three-dimensional map of our neighborhood. And most of the stars you see at night are so far away, it's taken a few hundred years for light to get there. So people over there would not see us, but they might see the Boston Tea Party, for example. And then we've, of course, also learned that all of this, which is what the universe was when my grandma was a teenager, is now just really a small, small part of this much, much larger object that we call our Milky Way galaxy, where it takes about 100,000 years for light to traverse from side to side. And this galaxy, too, is just something which is a small part of something much, much larger. And if we pretend for a moment that the speed of light is infinite, let me take you for a little drive through the intergalactic neighborhood now. Here, too, we see even larger structures, galaxies coming in clusters, superclusters, the gigantic filamentary patterns. And by now, we're hundreds of millions of light years away from Earth, so if we turned around and looked back, maybe we would see some dinosaurs if we could. And It's not even clear I'll be able to find my way back here because it looks kind of the same. So we've gradually learned as humans that there's just much more opportunity out there for future expansion than we ever dreamt of. And they can be more, parallel universes, etc. Now, what about our place in time? Here, too, cosmology has really shifted and expanded our horizons in a major way, because we know, when we look out into the sky, that since it takes a lot of time for light to reach us, the farther away we look, the farther into our past we're gazing. We can see a lot of things which happened 10, 11 billion years ago, and by looking at things at different distances away from Earth, we've been able to piece together the following story of what's going on with our place in time. We know that about 13.7 billion years ago, something really weird happened. We have no clue what it was. We call it our Big Bang. We have some ideas you can ask me about, but we have a very good idea of what happened in the 13.7 billion years since then, where gravity and other well-understood physics has both expanded our universe, cooled it off, and gradually transformed this rather uniform, boring hydrogen gas into all the interesting complexity that we're marveling at today. And going forward, we're going to keep expanding for a while. What's next depends on what the dark energy is doing, which dominates our universe with 75% of its mass. About 75, if I had to bet money, I'd put about 75% of it on the big chill, that we're just going to keep expanding forever, which is kind of dull. But the dark energy might, since we don't know what it is, dilute away and go negative, causing everything to come crashing back on itself again in a big crunch. Or the dark energy might turn out to anti-dilute and end up with an infinite density some finite time from now, ripping everything apart in a big rip in maybe 10, 20 billion years. Or we can have a big snap, something I have worried a bit about, where it might turn out that the very fabric of space itself just can't be stretched indefinitely without something bad happening. There are more mundane things which are going to go wrong sooner, like our sun is going to run out of juice in about 5 billion years. But it's very clear that unless we mess up ourselves here, there's a huge potential also for future time at our disposition. When we try to make the best of our universe, we have to talk a little more first about what exactly we mean by our universe. So when I first heard the word universe as a kid, I assumed people were talking about everything that exists. That's not what we mean in astronomy. We mean because when I look farther and farther away, there's only so far I can see. Eventually, I look so far away that things are so hot and dense that the hydrogen that fills intergalactic space is opaque. And it looks like I'm staring into an opaque wall, a plasma screen. And of course, it's going to appear to me the same way in whatever direction I look. So it seems like beyond all the galaxies, we see this plasma screen. We photographed it now in great detail. We call it the cosmic microwave background. It's given 2 Nobel Prizes so far. And it is the iconic image to me of our universe. I've had a lot of fun with my colleagues making this image by cleaning out the radio noise. This is it. And this is also something you can think about is roughly the sphere in space from which light has had time to get here so far since our Big Bang. Is that everything that exists? Almost certainly not. Pretty much all of my colleagues take for granted that space continues outside of this. But if we ask what we humans can go out and colonize and take advantage of, this is it in practice, give or take a little. Okay, so let's summarize the cosmic perspective and focus on the implications now for life and its future. So traditionally, we humans are very obsessed about our planet. I'm telling you that there's 10 to the 59 times more volume available. So we tend to obsess a lot about what's going to happen in the next 50 years, especially in our lifetime or in the next election cycle if we're a politician, or before the next quarterly report, depending on your job. And I'm telling you that there's billions of years available. Even when the sun dies in 5 billion years, if you ask me afterwards, I'll tell you how we can get around that little hiccup. or if you're worried about asteroid strikes. There's a lot of future. There's a huge potential, basically. And we humans tend to think about ourselves traditionally as the pinnacle of evolution. So let me just graphically illustrate what I'm talking about here. A short animation from our friends, very scientifically realistic. For being shown on TV, it's actually remarkably accurate. And it illustrates very nicely also the interconnection between life here and space. Where 60 million years ago, space had an impact on us, even very directly. We were basically, these little wee mammals were just running around trying not to get stepped on, basically, when we had this giant asteroid impact off of the coast of Mexico, and that was our lucky break.
What took you so long?
So the traditional view is that Homer Simpson and the rest of us, we are the pinnacle of evolution. We are the end of evolution. And the interesting question is, how did we get here, and how can we get better cell phones and stuff? What I'm telling you is, from the cosmological perspective, you ain't seen nothing yet. It's completely ridiculous to think that we humans, after evolving for 100,000 years or a million years, depending on where you count the start point, are the final, or the most advanced way in which you can put together elementary particles into something self-aware, and that this is the end somehow. If we actually have billions of years ahead of us, and if we manage to not screw up here, if there are life forms around in billions of years, they are likely to be as different from us, as far ahead of us as we are far ahead of bacteria. So I think it's very important to not shortchange ourselves and underestimate the potential of life in our universe. And at the same time, I think that's exactly what we're doing. Since I'm a professor, I can't help obsessively giving grades to everybody all the time, and I'm going to give a grade of D- so far for how much attention I think we humans are paying to what's known as existential risk. We've heard a lot of cheerleading, brouhaha, about how good things are going and how everything's getting better at this conference, showing a lot of statistics, which is correct. There are a lot of things that are much better, but none of these speakers have talked about existential risk, about the possibility that we might just completely wipe ourselves out. And I don't know any better than you do what the probability is in a given decade that we will completely blow it, but it sure isn't zero. We know plenty of things now about accidental nuclear war, about ways the singularity could go wrong, et cetera, biotech disasters, which suggests that, maybe it's 10 to the minus 4 probability per decade, maybe it's 10 to the minus 1, we don't know, but we ought to be thinking a little bit about it, and arguably the fraction of our GDP we should be spending thinking about this ought to be something like this fraction. Maybe you spend 1% of your income on health insurance and stuff, because that's roughly the probability that you will go extinct per year. And likewise, we humans, I think, are not really paying as much attention as we should to this. If we look at the long-term perspective, if we look at 50-year perspectives, who cares about a small risk per decade? But I'm talking about the future of the universe here. Good. Now, are we alone in our universe? That's a very important question if we want to know how significant we are and how relevant what we do is. this is a question I love asking people, and pretty much everybody says the same thing. They'll say to me, oh, I'm sure there's life out there somewhere else. I'm going to be the man to give you the minority report and give the contrarian opposite answer. I think, in fact, we are probably alone in our universe. And let me explain this a little more. Why do people usually assume that we're not alone? Well, people typically say, well, you know, there's just so much stuff out there, you know, there's got to be life somewhere, you know. Look at the sky map here. This is stuff we've done, me and my friends on the Sloan Digital Sky Survey. Let's zoom at any random point here in the sky, you know, and look how much stuff there is, you know. And we can zoom in like this anywhere we want in the sky. Surely somewhere, even if it's very unlikely to get life, it's going to happen. So let me give you the counter-argument. Let's get a little bit quantitative here. Francis Drake wrote down his famous Drake equation in 1961, where he simply pointed out that in order to get intelligent life, a lot of things have to happen. So the probability for the intelligent life is the product of a lot of different things. Now, back in 61, we'd had no clue whether most stars had planets around them, or whether this was some kind of fluke that happened in our solar system. But now, actually, we know a lot more. We know quite accurately the rate of formation of stars. We know that planets are actually very common. In the last couple of decades, we've now, as of 2 days ago, found 693 extrasolar planets. We have not gotten to the point where we can get images of them like this, but it's very clear that there are plenty of planets just like Earth in our own galaxy, many of which were formed billions of years ago. Okay? So that's not a problem. However, there are other things here, further down the list, where I think it's fair to say we're still completely clueless about what the probabilities are. For example, to pick one example, you know, the ribosome. It's a super important part of the machine that's me, you know, the thing which is making my proteins by reading messenger RNA. It's a complicated machine. This is just showing you one little subunit of it. How do I build my ribosomes? Well, by using another ribosome that I have. So to get the first ribosome, it could be that it's actually kind of easy, because for reasons we don't understand, maybe it can happen through many, many steps in evolution that are each useful, or maybe it's not. I think the fair thing to say is we really don't know. We also don't know whether you automatically go from snails to intelligence, or whether that's an unusual step, an unlikely step. So we just heard from Eliezer here that anyone who's not a Bayesian is evil. So I'm going to embrace the religion of Bayesianism and say I have no clue about what this probability is. So I'm just going to assume what we in geek speak call a uniform logarithmic prior for it, which means that if I take the logarithm of the probability, any number is equally likely, which also in plain English just means it's equally likely that the probability is 10 to the minus 30, or 10 to the minus 20, or 10 to the minus 10, or about 1, to get intelligent life on any given planet, okay? And from that assumption, it follows directly that if I ask how far away do I have to go to that next intelligent life out there in space, that also has a log uniform prior. So it's equally likely that the distance I have to go down to find intelligent life is 10 to the 40 meters, as 10 to the 30 meters, 10 to the 20 meters, 10 to the 10 meters, etc. Let's look at some data. What do we know about this? Well, here is indeed distances away from Earth on a logarithmic scale. So I'm saying, a priori, without looking, we think it's equally likely that the nearest intelligent life is here, 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 anywhere out here. And this continues. I could walk for miles, because we have an enormous amount of space out there. And if the probability is 10 to the minus 80 to get life on a given planet, you have to go very, very far, right? Now, we can only see intelligent life. To have intelligent life in our universe, it has to be less than 10 to the minus 26 meters away, because that's the size of our universe. Moreover, we all have had it. I am quite sure that there is no life within our own galaxy that's mastered space travel, because if there were, we would have the Fermi paradox. They would have been here already. if they've had billions of years of head start, and it only takes light 100,000 years to traverse our galaxy, it's not that hard to get here. Come on. It's not, I can't say it isn't rocket science, because it is, but rocket science isn't that hard in the grand scheme of things. There are a lot of counter-arguments to this, which I find generally flawed. Some people say, well, you know, maybe all the aliens are like just love and peace and motherhood, and they don't want to travel to other planets, or maybe they all want to just introspect and play computer games, and we don't notice them. But let's remember here, natural selection. All you need is one single alien species who's not so into peace and love and motherhood and decides it's really cool to go colonize everything, right? And we would have noticed. And any other species that has any self-preservation instinct has to deal with it. So I think it's pretty clear we're alone in the galaxy. So if there is intelligent life in our universe, this distance, you know, which we're assuming is random to the nearest neighbors on some huge scale. It could be out here, it could be here, it could be here, has to lie in this very narrow range of just 5 orders of magnitude from edges of our galaxy to edge of our universe. And I think that's not so likely. So suppose I'm right. Suppose, in fact, we are alone in our universe at our level of intelligence. That means that life is very rare, right? Why is it so rare? There must be some kind of roadblock somewhere along the way. There must be some kind of roadblock to not have aliens already have come here. We have to have some roadblock between just making very simple life, making planets, to getting the spacefaring aliens, whether interstellar nanoprobes, whatever. Where is the roadblock? It's a very, very important question. There are 2 basic possibilities. Either, you know, the roadblock lies before us in this evolutionary stage. Maybe there was something tricky about the ribosome or something else to do with getting very simple life. Maybe it was hard going multicellular or whatever. Maybe it was hard going from snails to some snail-like things to intelligent beings or like us. Maybe there's a roadblock after us instead. Maybe it's easy to have it like this. Maybe a lot of places where you get conferences held, but then for some reason we don't notice them because they all self-annihilate quietly. Or maybe it just turns out for some reason we don't understand to be impossible to do interstellar space travel. Whatever. There could be some roadblock here. It's clear there is a roadblock there or both, right? Where is it? Well, I would recommend that you all cross your fingers and hope that the roadblock is before us, not after us. Because if the roadblock is after us, we're basically screwed, at least with our more ambitious visions, right? We're forever landlocked on this planet. We're never going to be able to go take advantage of all these wonderful opportunities for reasons we are about to discover. But if the roadblock is before us instead, that would explain very nicely also why we're alone in the universe, why we haven't been visited. We're already past it. We don't care that we're rare. We made it, guys, okay? Here we are. And our future is only limited by our own imagination and our ability to get our act together. Which is not so only, it's a big if, but still, it's a lot better. So I actually hope, whenever we do searches for life elsewhere, I hope they're going to fail. I get so happy every time my colleagues tell me that we have found no life on Mars, and that we've picked up no sign of any independently evolved life anywhere else in the universe. And because if they did find that, that would suggest that the roadblock is not here, right? If that's so easy to do, that it happens several times even in our solar system or nearby, right? That makes it much more likely that the roadblock is in front of us. So don't think of that as bad news next time someone says they couldn't find any sign of life on Jupiter's moon, Europa, or something like that. You should be happy and think that's good for us. All right. So to summarize all of this, the cosmic perspective on the future of life, here's what I've been saying. First of all, we have huge potential. 10 to the 57, we've only used up 1,000,000th or less of the time we have. We've used up only 10 to the minus 57 or so of the volume we have. So that's great. That's the good news. The bad news is we have great challenges. First of all, we may be the only starting point, I think we are, in our universe for life. So there's a heavy responsibility. We might feel a little bit of performance anxiety and stress about this. Second, it's clear that there are various ways in which we could destroy life here. And again, maybe it's 10% per decade, or maybe it's 1,000th of a percent, who knows. But we should worry about it. I think we can all agree also that the number of convincing long-term plans that we humans have come up with and agreed upon for dealing with existential risk is a big round number, 0. And by a very crude estimate, the fraction of the world gross domestic product dedicated to existential risk is about 10 to the minus 6 or so. I'm being kind of generous here, okay, which is way, way, way less, for example, than the $20 billion that the US spent on air conditioning for troops last year. So, sure, I don't mind if people don't have to sweat so much in their tents or whatever, but let's not do that at the expense of this kind of existential risk. So that's why I'm giving it, for my Existential Risk Management 101 here, I'm giving humanity a D- grade. I think we should all ask ourselves, what can we do, in Peter Thiel's spirit, to draw more attention to existential risk and to channel more creativity, more resources into helping us realize our cosmic potential, rather than just be so short-sighted. Let me give you just one example of something I think is very pertinent to this conference, to do with information. Why do we humans make so many stupid decisions? Well, to make good decisions, you want to have the right information available when you make the decision. And I often wish that my brain would be kind of like my laptop, that it would put up a little window, Like the other day, I did a golf swing, and I hit the ball right into the lens of a camera of a guy. Bullseye hit. I wish there would have been a little window that popped up and said, Max, are you sure you want to hit this ball so hard? Click yes, no, cancel, But often we don't have information in the heads of the people who are making the decisions when they need it. So to get information, this is how I think about the flow of information in the world. Information can be in 3 different states. To be useful for decisions, it has to be in the head of the person making the decision. It has to be known to that person. But information can also be instead in the state of it that it's private. Maybe Eliezer just discovered something cool, and he has it in his head and hasn't told anyone else. And it's not in the head of the person who's going to make the decision. Then it can be disseminated, which is a step forward, making it public, which means online these days, so that someone actually actively looking for it through research can find it. Or there can be a feed-forward process where the information is copied from the public domain into people's heads through education or marketing or journalism. And then there could be research, of course, which takes information in the heads of the researchers and creates new information out of it. And there are many different things that can go wrong in this. And every way in which you can improve working to this triangle, I think, is a step in the right direction for the future of life. I've had a lot of fun talking with Michael Vassar about this, and there are many impediments, of course, reasons why you might fail in information creation. People might not be motivated. There may be a lack of time, lack of resources, fear of criticism. Christoph Koch was joking about how people had cold water poured on them for researching consciousness. It's an example of that. You might have a misguided approach to doing the research. There are also many reasons why you might fail here. It could be you might not publish things because you don't have time, you're not motivated, you don't have access, or there's some kind of censorship for uploads or downloads. I think the third link is where, in a way, there's the most low-hanging fruit, where it's just crazy how poorly this era works in some context. For example, last year in Haiti, 12 people were burnt as witches. I'm not talking the Salem witch trials here hundreds of years ago, or witch trials in Sweden, where I come from. I'm talking about last year. 40% of Americans believe that humanity is less than 10,000 years old. It's not like there isn't better information on Wikipedia about that, but somehow that information has not gotten copied into the right neurons. 3% of Afghans have internet, so obviously that causes some difficulties with this arrow. 92% in a poll done last year didn't know about the 9/11 attacks. So no wonder if some of them feel a little bit confused about what the US is doing there. I think there is a lot of great opportunities here by working on better education, less biased education, etc., trying to create less biased media, etc., to improve this flow of information here. And in particular, I think it's really striking how the people who are the most unscientific about implementing this arrow are we, the scientists. People who are trying to convince you that tobacco is not addictive or whatever the agenda is, will use the latest scientific research in marketing with all the hot chicks and everything and focus groups and so on, and figure out what's the most cost-effective way of persuading as many people as possible to have some information in their heads, right? But we scientists, we're like, no, I'm so snobbish, you know, that's beneath me, oh, I'm not going to stoop so low, you know. It's pathetic. I mean, it's like if I'm being invaded by an army of tanks, and I'm like, that's beneath me to fight with tanks. I'm going to fight the tanks with a sword, like a real Viking, you know. We scientists really have to get off our high horses, and if we really want to influence what information people have in our heads, we have to be scientific, not just in the way we create information, but in how we disseminate it, and use all the same marketing and focus group tools, and figure out what sound bites really work and tell them to the journalists, etc. This is too important for us to just not do because of some silly snobbish reasons. Okay, in the last few minutes, let me just wrap up by looking a bit further ahead again. So suppose we can get our act together and not immediately go wipe ourselves out. Suppose life in the future is able to, in some form or another, engulf the universe. Then there's another thing I'm really worried about. What if this is done by some future form of AGI, which we gradually evolve into by whatever process, and we're kind of happy about it because we feel that they've incorporated our values and they talk with us and they're nice to us and stuff. But suppose they're all zombies and just seem conscious. We heard a number of interesting talks that talked about the zombie problem. Now, how do you know if they're really conscious? Most of my colleagues, scientific colleagues, just don't give a hoot about this question. They think this is philosophy. I don't care if the thing is conscious or not because I can't measure it from the outside. I care a lot because of this cosmic perspective. You know, I feel that of all the traits that our life form, our human life form has, the one that's by far the coolest is the subjective consciousness. The fact that I feel that there's someone in here looking out on the world. And this is, if our universe gets engulfed by some future life which evolves from us, and it doesn't even have that number one trait, you know, I think it's just a giant waste of space as far as I'm concerned. And so to me, it could be very important that we understand consciousness enough that we feel we can answer that sort of question before we're willing to ever hand the torch to such life forms. And this leads to the very last question I want to address, which is, are we insignificant? It's quite funny. I'm just going to share my personal journey with you here because it's involved a 180-degree turn, actually. The more I learned about our universe, the more insignificant I felt. You know, we're so puny, you know, in this giant universe. We're so short-lived, you know, what's 100 years compared to 13.7 billion? We're not even made of the majority substance. There's 96% of other stuff that doesn't, dark matter, dark energy, doesn't even want to deal with us. You know, it's kind of depressing. But I've completely changed my mind on this now. If I manage to convince you that, in fact, you know, this is just me feeling crushed by the vastness of the universe here. Okay? If I actually managed to convince you, though, that we're probably the only life this advanced in our universe, then the picture becomes very different. Now, sure, the universe is bigger, but size isn't everything. Those galaxies that I find so beautiful to look at in my day job, why are they beautiful? They're beautiful just because we people are looking at them. You know, only we humans who give meaning to our universe. if there were no one looking at the galaxies, those galaxies would be just a giant waste of space. So I feel that in that sense, having the life that's self-aware in the universe is it's not insignificant. It's the only thing which gives any significance to anything. We're the most significant thing in our universe, in fact. So this Earth may be small, but we're a very significant place. We're the place that makes it all significant. What about time? Well, 100 years isn't a long time. Our lifetime isn't that long. But I think we're at a fork in the road, really, in terms of what's going to happen with the future of life. Because it's now, in our lifetime, we have the potential to just completely screw it and go extinct. We also have the potential in our lifetime to really get our act together and build towards a future which could ultimately make our whole universe alive. And if that happens, this decision base, I don't think we can muddle along like this at this fork in the road for too many more decades without something really bad happening. So I think it's very likely that it's in our lifetime that it's going to be decided whether we're going to just blow it or whether the whole future of our universe is going to be this marvelous living organism. If there are such living organisms in the future, if our future is alive billions of years from now, I don't know how they're going to think about us, but there's one thing I know for sure. They're not going to think that we're insignificant, because we were the ones who made all the difference. So go out there and make all the difference. Thank you very much.
We've got about 10 minutes for questions. Ten minutes for questions. Who's first? Here's a hand on the left side on the aisle.
Can entropy ever be reversed?
Can the entropy ever be reversed? That's a really fun question because, we've been taught since kindergarten that the second law of thermodynamics says that entropy always increases. But the truth is we don't really understand entropy once you include the cosmic perspective and gravity. If space can expand forever, no one has ever even been able to say exactly what the entropy of this infinite thing is. It's also very striking how we think of entropy as then generally making things more messy. If you have, say, a latte, you put some cold milk in, after a while it's all lukewarm. So you'd think our universe has been sitting around for much longer than your latte. It should be really lukewarm. Here we are, 300 Kelvin planet, 6,000 Kelvin sun, 3 Kelvin space, and we feed off of this and are able to live. That's because gravity actually increases this entropy by making things more complex and interesting. So, A, there are a lot of things about entropy we just don't understand, and B, the future of life is in no way limited by the second law of thermodynamics, in my opinion.
You must have gone to a great kindergarten. Next question here on the aisle on the right.
Yes, it seems to me that a key part of your argument for why we are most likely the only life forms in the universe is that if there were other life in the universe, then statistically speaking, it's likely that at least some of that other life would have predated us, and they would be sufficiently more advanced than us that they would have been able to come here and contact us. However, I would posit that they would have no motivation to interfere with us or to come here and communicate with us or notice us in a way that we would observe, and they would be sufficiently technologically advanced to be able to observe us without us noticing it. They would have no reason to try to colonize us because they would be sufficiently technologically advanced to be able to go and find an empty planet devoid of life and colonize that planet instead. And they would, out of curiosity, want to, well, let's see how these guys develop completely independently. And certainly it wouldn't make sense for them to interfere, because that would be like ruining the experiment almost. So they would be thrilled that here's this experiment, let's see how these guys develop. And actually, we may be that life. They may have come here a few thousand years ago and planted human beings on on here, and we may be that life from some other planet.
Yeah, those are all good points. I agree with you that it may well be that most advanced alien civilizations are this nice. However, I think since we have hundreds of billions of stars and hundreds of billions of planets in our galaxy, you know, if there are millions and millions of these, you know, all you need is one that decides, actually, you know, it's kind of boring just hanging out here. Let's turn the galaxy into a parking lot, or whatever goals they have. You know, it's kind of like we humans. If you know, most humans, if they see an ant on the street, are not going to like step on it on purpose. They think it's cute, you know. I sometimes even, I have to confess, like take earthworms off the sidewalk and put them in someone's yard so no one should step on them, you know. But at the same time, you know, if a company finds oil in some place, huge oil find, they want to put a rig there, and then there's some ants who happen to be there, you know, tough luck for the ants. And in this situation, we are the ants. So.
They were self-destructive. If they were that technologically advanced and they were evil, I mean, once you evolve beyond a certain level of technology, you are going to kill yourself via nuclear destruction or some other type of destruction if you haven't evolved morally. I mean, it's impossible for life to go. It's impossible to evolve beyond a certain point technologically.
Well, I hope you're right. I just think
the argument
we have
is
to be
that
very wary of engaging in wishful thinking about things we really don't understand at a fundamental level. So I'm not saying it's 100% sure we're alone, but given how many different planets there are there that are much older than Earth, I'm still putting the vast majority of my money on that we're alone. And if you want to take the bet, I'll be happy to make it.
next question over here on the right on the aisle.
As it regards the statistics that you cited for us having gotten over the issue that it's happened already and not in front of us, the obstacle in our evolution, what does that say for the possibility, and then consciousness maybe is the result of that? What does that say for the challenges associated with the development of artificial intelligence? Because if we've gotten over the obstacle, and that's where the statistics lie, and it hasn't happened anywhere else in the universe, then how difficult will it be to create artificial intelligence that mimics us to a certain extent?
Yeah, so I think that my guess is that if the roadblock really was in front of us, in back of us, so that we've already passed this great roadblock, then I think it's quite unlikely that there is a roadblock in the future. You know, the interstellar space travel is ironically kind of the simpler question of the two. And as a physicist, it's an engineering problem. It's not any fundamental problem. The much harder problem, of course, is creating an AGI, which is conscious and so on. But there again, from a physicist's point of view, you know, okay, so here's 10 to the 28 atoms put together in a special way. You know, there's no law. I very much doubt that there's a fundamental law of physics saying that this is the only way to put together that many atoms into something conscious and self-aware. I'm sure there are many, many other ways which are much more interesting than what you're looking at right now. So the only question then becomes, well, are we humans, clever enough to find it? And I'm an optimist in that. And at a minimum, I would say that there's no better way to guarantee failure than to convince ourselves that we can never do it and therefore not try. So if we're going to fail with that, I think we should at least go down swinging, trying our best.
One back here.
This is not a question so much as a comment on the first questioner who asked whether entropy can be reversed. You were supposed to ask that question last.
I know, sorry.
Back on the right side, several hands. Okay, go ahead.
Yes, even if we are the only sort of intelligent life form, what's to stop a future version of us from like 1,000 or 1,000,000 years from now returning back in time to visit the Earth?
Time travel. I love this question. So, what do we know, first of all, about time travel from the point of view of state-of-the-art physics? We know that forward time travel is easy. It's just an engineering problem, you know, go near the speed of light. Or in practice, what's much easier is find a black hole in the neighborhood. And there's a very cool orbit I call the tourist orbit, where you're exactly twice as far out as the event horizon. You can orbit around there, and you're going near the speed of light. And when you come back, your friends are going to be like, "What vacation was that? You look so youthful." And you'll be like, "Dude, it's because I'm younger than you." Backward time travel, a lot harder, probably impossible, but it's fascinating to me that we've still failed to rigorously prove that it's impossible to do that. The best shot, I think, the least unpromising model is probably the wormhole, where you have something which looks a bit like two black holes that are connected basically with a shortcut through space-time. You jump in here, you come out there instantly. If you can build a stable wormhole like this, it's a great intergalactic subway system, you know, to go fast between places. And you can easily convert that into the time machine you need. You take one end of the wormhole and put it into this tourist orbit around another black hole for a while. So now it's aging slower than the other end. Now you take it out, you put them together, jump in here, you come out 1 year in the past, go through this way, you come out 1 year in the future. And you could even build a whole network of these. So you have like the 1 year machine, the 2 year machine, the 4 year machine, the 8 year machine. It's kind of like you take the A train and then the B train and the E. So if you want to go, you know, 7 years back, you take the red line and then the green line and the blue. The problem with the wormholes is that they seem to be very unstable. And if you jump into the time machine and it collapses into a black hole, it's a bit of a bummer, right? For a long time, people said, "Oh, you can never do this because the only way you can stabilize them is if there's some really weird kind of substance which has like negative pressure and other stuff, and that obviously can't exist. Except, oops, you know, now we found dark energy, which has many of these weird properties and makes up 75% of the universe. So we shouldn't be so arrogant and say we can't do it, even though, again, I still wouldn't bet my money on it. The one other catch is, suppose we can build a time machine for backward time travel and we inaugurate it tomorrow in the opening session of this conference. That's as far back in time as our descendants will ever be able to go. It's just like you can never take the A train, you know, past Far Rockaway, because that's where the line ends. So what might happen is tomorrow at the opening session, we turn on this time machine and immediately some really cool-looking aliens come out and kill us with some funny-looking guns or something. But at least the good news is we're still safe today. Thank you.
That's a great note to end on. That's all the time we have. Thank you very much, Professor Tegmark.
That was awesome. Thank you.
So that's the end of day one. Come back tomorrow. Day two starts again at 8 a.m. Breakfast will be available at 7. Bring your tickets, bring your badges, bring your smiles. We'll see you bright and early tomorrow morning.